Hey kiddos, welcome back to Allen High School's discussion of oxidation numbers, review of naming, and covering net ionic reactions. Quick little introductory segment of things that we've learned in Pre-P. Our first few chapters are almost all review. Now, we were talking about oxidation numbers and the rules, and I want to work some examples to help you out with that. In our first example, we have hydrogen. Hydrogen is all by itself, not bonded to anything, so it has a 0 for its oxidation number. Zinc is all by itself, not bonded to anything, so it has a 0 as its oxidation number. Now remember, earlier I said we want to assign firm rules first. So if you do your firm rules first, you'll be in much better shape when you get to the final results. Now, rubidium's group 1, so it's always +1. You could calculate the sulfur if you wanted to, but it's with a metal, it's an ion, so you make it its ionic charge. The ionic charge for sulfide as an anion is -2. Now, this next one, I'm not even sure this substance exists, frankly, but we're going to do it anyway. Phosphorus here, phosphorus is phosphide. It's the negative anion, and that's -3 because it's group 15. Now, chromium has a whole slew of oxidation numbers that it can take on. So we're going to need to calculate that chromium. So let's do a little algebra. We have 3 chromiums. We don't know what its oxidation number is. Right? We have 4 phosphorus, but we know that that phosphide is -3. And since there is nothing indicated in the upper right hand corner, the sum of those oxidation numbers is 0. So if you solve for the chromium, you should get +4, which is unusual. Chromium's usually +3 or +6. Okay? Now the next one is barium nitrate. I've likely already warned you in class, but you are going to have to rememorize those polyatomic ions. Now, the tricky little puppy here is the nitrogen, and you can either do it as the nitrate ion separately or in the whole compound. I'm going to do it in the whole compound. Barium's group 2, so it's +2. Oxygen is not all by itself with group 1, group 2, hydrogen or fluorine, so it's -2. And now we'll need to calculate the nitrogen. I have 1 barium, and it's +2. I have 2 nitrogens. Remember that nitrogen distributes, so I have 2 nitrogens, and I don't know its oxidation number. I have 6 oxygens, again distributing that 2, so I have 2 nitrates. They each bring me 3 oxygens. Now, the sum of these is again 0. And if you solved for the nitrogen, you'd come up with +5 for that nitrogen. All right, let's try the next one. Hydrogen is not all by itself with a metal, so it's +1. Oxygen is not all by itself with group 1, group 2, or hydrogen or fluorine, so it's -2. And now we have to calculate the phosphorus. Phosphorus can be -3, +3, and +5 commonly. And so we have to figure out which one of those that phosphorus is. If you have a central element of 3 elements, you're going to have to calculate it. So I have 2 hydrogens. They're each +1. I have 1 phosphorus. I don't know what it is. I have 3 oxygens. They're -2. Now this time I do have leftover charge, and when you have leftover charge, you have to set that sum equal to the remaining charge. So we find out that in this case the phosphorus is indeed +3. So that was our choice of our possibilities. Now we're going to practice these in class, so hopefully you're picking up quite a bit from the video notes, but remember, mastery comes after we practice in class. Bromine's the most electronegative. It's going to be actually a bromide, so it's -1. This is a non-metal, so this is a covalent substance. So you make the most electronegative as negative as it can be. So that means if you did your algebra, phosphorus would be plus 5. Chloride's minus 1. Phosphorus is plus 3. Let's just do a few more. Chloride is closer to fluorine. It's more electronegative, so it's plus 1. Do a little calculation, and you get plus 3 for iodine. Iodine can actually be minus 1, plus 3, plus 5, or even possibly plus 7. So those little groups, their oxidation numbers can get a little wacky. Let's try the sulfur. Oxygen's more electronegative, so it's -2. Let me model a way to do that algebra a little bit more quickly. If each oxygen's -2, I have a total of -4. Now, since there's no charge, that has to equal 0, which means I need a plus 4. There's only one sulfur, so each sulfur has to be plus 4. All right. Let me model that again with this KMNO4. KMNO4. Let me show you how I will often do this. Each oxygen, so I put the individual on the top, is -2 for a total of -8. Potassium's group 1, it's plus 1. There's only one of them, so I have a total. So I put the individual on the top, I put the total on the bottom, and this has to equal 0. Well, if you do your algebra, I need a plus 7 in here in order to make that 0. There's only one magnesium, so the magnesium has to carry the whole plus 7. So that's plus 1, plus 7, -2. It's the individual that we're after. Now, finally, I'm just going to do these two. I want you to really note carefully. There's a difference between the nitrate ion. Each oxygen is -2, which leaves that nitrogen being, excuse me, not plus 4, but plus 5. And nitrogen trioxide, which would leave nitrogen at plus 6. Not a very stable or happy position for nitrogen to be, but we wanted, sometimes we just put in substances that aren't real common just to show you the process. And I wanted to make that process clear to you. Okay, so we've done some oxidation numbers. Now we're going to get into naming and formula writing. So until then, this is signing off.